we have now come to a right understanding of the concept of a universal abstract set, of subsets of that set, and how to build, via set operations, more complex subsets from existing subsets. The key operations are unions, intersections, and complements. Now, with these under our belts, we can actually now do some algebra on the sets, and in a particular form that we shall talk about shortly. So here is a basic idea. When I say algebra, what comes to mind? Well, when we do arithmetic or algebra, we realize, well, we add, we multiply. Okay. When we add, a key element is the idea of a zero. If you add a zero to any number, you just keep that number. When you multiply, a key element is a 1. If you multiply any number by 1, you get back that number. In the structure of sets, we have specific sets which have these properties, and these play the roles of a zero and a unit in the algebra of sets. So, if one takes, let's say, a subset A, and again we have in mind an abstract universal set, uppercase omega, lurking in the background, as it were. If you have a subset A, and you take its union with the empty set, well, what do you get? Well, naturally enough, the empty set has got nothing in it. A union just expands by pulling in everything in both the sets, but the empty set has nothing, and therefore you retain the original set. The empty set plays the role of a zero. Taking the union with the empty set does not change the original set. What happens if we take the intersection of your set A with the entire universal set omega? Well, since every element of A is in omega, manifestly, then the intersection contains every element in A and nothing else. In other words, the intersection of A with omega is A itself. Omega stands in the role of a multiplicative unit. Oh, very good. So it looks like we have things which correspond to a 0 and a 1. What about additions and multiplications more generally? What are the key properties that come to mind when you talk about addition and multiplication? Naturally enough, we can add in any order and we can multiply in any order. And this is what is key about addition and multiplication. Now, take the time to write down the identities I've given you on the screen. Ponder them for a while, and when you're ready, let's deconstruct them. Make sure we come to a right understanding of what these very basic identities represent. Now that you're back, let's take a look at the very first identity I've shown you. The assertion is that A union B is the same as B union A. Now, I will put it to you that this is manifest and trite. We could do a formal proof of this, but it is hardly worth the effort. Let us, in words, picture what A union B is. It is a collection of elements little omega, which are in A or in B or in both. But if they are in A or in B or in both, they belong to the ensemble. It does not matter which order I specify A and B, does it? In any case, omega is going to be in A or in B or in both, and therefore A union B is the same as B union A. You can do unions in any order without changing the outcome. And the same thing holds manifestly for intersection. A intersection B is the set of elements omega which lie both in A and in B, or, in other words, which lie both in B and in A. In other words, A intersection B and B intersection A are exactly the same sets. Unions and intersections can be done in any order. Of course, this in algebra and arithmetic is what we call the commutative property of addition and multiplication. Just like addition and multiplication, unions and intersections are commutative. Now, what we go beyond two subsets? Suppose we throw in a third subset. Naturally enough, I'm going to call it C. Again, bear in mind there's an abstract universal set in the background. A, B, and C are purportedly representing subsets of the universal set. One could draw a Venn diagram here, but of course it's getting more complex here to show the various interrelationships between the three objects. If I have three such subsets, I could function as follows. First, consider the particular subset obtained by taking the union of B with C. Well, that's a set. What if I take the union of that set with A? And to clarify that here's the order in which I'm doing things, we naturally enough use parentheses. We use round brackets to say, first take the union of B with C, and then take that set and take its union with A. Now, the assertion is that you would get exactly the same set if you first took the union with B, A with B, then took that set and took its union with C. Now, again, this is almost so trite as to be not worth mention. All we have to do is keep in mind what is happening once I do all these unions. The result in either case is a sample point omega, which is in A, or in B, or in C, the ors being not exclusive, meaning that they could be in both A and B, or both A and C, or both B and C, or perhaps in A and B and C as well. But this description of omega is the same for the quantity on the left as well as the quantity on the right. Therefore, these two ways of describing this composite set must be the same. Exactly the same kind of argument works when you talk about intersections. The intersection of B with C intersected with A is the same as the intersection of A with B intersected with C. In both instances, I'm talking about sample points omega, which lie in all three of A, B, and C. This, of course, is what in ordinary arithmetic we call the associative property of addition and of multiplication. So, unions and intersections are commutative and associative. In other words, you can do them in any order. Now, once you understand that I can do an associative property with 3 sets, I can do it with 4, with 5, with n sets. And of course, very quickly, we are running out of symbols in the alphabet. We captured this abstractly. Naturally enough, one of the ways of doing this is to use subscripts 1, 2, 3, 4, 5, up till, say, n for some finite number, to connote which subset we are talking about. So, A subscript 1 will be one such subset, A subscript 2 will be another subset, A subscript n will be the last subset. N is any fixed but arbitrary number. Suppose I'm given n such objects. We can think about taking the union of the n of A1, union A2, union A3 through UAN. And again, the order in which we do these unions does not matter. We could simply write them down in a long stretch of unions, A1, union A2, union A3 through union AN, without bothering to group them with parentheses. Exactly the same thing can be said about intersections. A1 intersection A2 intersection A3 through intersection AN. Again, without parentheses, there is no ambiguity. In such settings, we will use a generic letter like I or J or K to represent a typical member. So we'll say A with a subscript I is a generic, the ith subset in a finite collection, or perhaps even in a countably infinite collection. And in this context, it is completely reasonable to say the union of a finite or infinite collection of subsets AI is just write down the union symbol, the smile, the cup pointing upwards. Take the union as I varies over a finite or an infinite range of the A sub i's, and there will be absolutely no ambiguity. This represents the collective union of a finite or a countable infinity of these sets. Similarly for intersections. Simply write down the intersection operation, the frown or a cup pointing downwards, the intersection over all I ranging over a finite or a countably infinite collection of subsets A sub I just stands for the intersection of all of them, and again there is no necessity for grouping parentheses. Okay, this kind of simplicity in mathematics, of course, makes it easier to write down equations without getting stuck with a lot of pettifogging detail. Good so far. Now we've got through the commutative and associative properties of unions and intersections. Multiplications and additions can be done in any order. There's one more property, and this is what we call the distributive property of multiplication over addition. 2 times 3 plus 5, notice I'm grouping 3 plus 5 first and then multiplying it by 2, we know is the same as 2 times 3, to which we add 2 times 5. Multiplication, we say, distributes over addition. And again now, here's a simple analog when you talk about unions and intersections. Say again, we are dealing with 3 subsets, A, B, and C of some universal set omega. Form the intersection of B with C first. We know what that means. The set of elements common to both B and C. Suppose I take the union of that with a third subset A. The claim is that you get exactly the same set by first taking the union of A with B, then taking the union of A with C, and intersecting them. It's as if unions distribute over intersections. We could do exactly the same thing by reversing the intersection and union operations, and here already is one point of difference between ordinary arithmetic. Multiplications distribute over additions, but additions patently do not distribute over multiplications. But in the case of sets, unions distribute over intersections. Intersections simultaneously distribute over unions. The intersection of A with B union C is the same object, the same set, as obtained by intersecting A with B first, then intersecting A with C, and taking the union of those two. Now, what I've shown you is 2 operations, unions and intersections, which have the familiar features of ordinary arithmetic addition and multiplication. Unions generically loosely standing in the role of an addition, intersections standing in the role of a multiplication, very loosely. These operations have analogues to the idea of a zero and a unit. In this case, the empty set and the universal set. These operations are commutative and associative. You can do them in any order. These operations distribute one over the other. Now, there's this old adage, if it walks like a duck, if it quacks like a duck, it's got to be a duck. And similarly, if it walks like an algebra, if it quacks like an algebra, it's got to be an algebra. We call this an algebra of sets, and we draw freely upon the idea of algebras that we are already acquainted with in ordinary number systems. Okay, now here's the first place where we now actually have many theorems, identities, formulae, but these are basic and important. We should start with these, and just as in ordinary algebra, the next question then is, well, can I prove deeper results? Are there more subtle results which are not immediately apparent that I can use these rules of algebra to discover? Well, of course, there are very, very many in the theory of sets, but we'll need just one. Okay? These, again, are familiar to those of you who've taken logic or Boolean algebra. These are called De Morgan's laws. Right. And let me start with the simplest of these settings. Let's start with 2 subsets A and B of a universal set. Let's start by forming the union of A with B, that's a new set, and let them take the complement of that union. De Morgan's law asserts that the complement of A union B is the same as the complement of A intersected with the complement of B. You have a dual statement when unions and intersections are interchanged. If you start by intersecting A with B first and then take its complement, that is exactly the same thing as taking the complement of A and taking its union with the complement of B. I won't pause to prove these now, though you should pause and see if you can sketch out to your satisfaction a proof or a sketch of ideas which makes this convincing for you. Draw a picture. Ask yourself, what is the complement of A union B? And then ask yourself, what is the intersection of A complement of the B complement? Can you convince yourself you've got the same object? Do the same thing with unions and intersections reversed. And when you're ready, come back. Well, at this point, I'm going to defer trying to show you a proof. Eventually, I'm going to give you a ammunition where you can construct a proof for yourself. This is simple, it's not difficult, and you'll be able to do it quickly. But let's very quickly expand on this idea. The basic idea behind De Morgan's laws is the following: that if you take a union of a bunch of objects and then complement it, it is the same thing as taking the intersection of the complements. Similarly, if you take the intersection of a bunch of objects and then complement it, that is the same thing as taking the union of the complements. And let's very quickly provide mathematical notation capturing this intuition. And you should pause and again write it down. In these expressions, I am starting with a family of subsets A subscript I. I is going to run through a finite range, perhaps 1, 2, 3, 4, 5 till 10, more generally 1 through n, or I could run through a countably infinite range. For example, I could run through all the natural numbers, 1, 2, 3, 4, 5 ad infinitum, or I could run through all the integers, 0, 1 minus 1, 2 minus 2, and so forth. I runs through a finite or countably infinite range. And we immediately have analogues of De Morgan's laws for countable unions and countable intersections as well. These turn out to be hugely important and useful. Bear these in mind.